The cosmos you see is a magnificent illusion. There are profound, hidden layers to reality that our senses cannot perceive, and the true nature of the universe is far stranger than it appears. We are about to journey through 30 mind-bending theories that peel back the veil, from holographic projections and parallel worlds to the possibility we live inside a simulation. By the end, you will possess a new framework for understanding the deepest mysteries of existence. We will uncover why time might flow backwards and if our entire cosmos fits on a two-dimensional surface. What single question about reality keeps you awake at night? This first theory suggests the universe itself might be a cosmic hologram. Our experience of a rich, three-dimensional reality, from the vastness of space to the solidity of the ground beneath your feet, could be a grand illusion projected from a two-dimensional surface at the edge of everything we know. Think of the hologram on a credit card. That shimmering, three-dimensional image is not actually deep. It is encoded on a flat, two-dimensional piece of plastic. The holographic principle applies this same logic to the entire cosmos. It proposes that all the information needed to describe every star, every planet, and every one of us is painted onto a distant, two-dimensional boundary, and our three-dimensional world is just a projection of that data. This bizarre idea emerged from a deep puzzle in theoretical physics known as the black hole information paradox. When something falls into a black hole, according to our current understanding, it seems to be lost forever. Its information, the fundamental data that describes what it is, vanishes. This violates a core principle of physics, which states that information can never be truly destroyed. The holographic principle offers an elegant solution. It suggests that the information of everything that falls into a black hole is not lost inside its mysterious interior. Instead, it is smeared and stored like a cosmic fingerprint on the black hole's two-dimensional event horizon, the point of no return. The three-dimensional space within the black hole is just a projection of that information. This reshapes our very conception of space and time. If this theory is correct, then the solidity and depth we perceive are not fundamental properties of the universe. They are emergent phenomena, a consequence of how information is processed and displayed. The fabric of reality might be far more like a video game rendering a three-dimensional world from flat code than we ever suspected. What other illusions might be hiding in plain sight? If the information encoding our reality is truly a surface-level illusion, then what about the reality itself? This brings us to a theory that stretches the concept of existence to its absolute limit. The Level 1 multiverse proposes that our entire observable cosmos, with its hundreds of billions of galaxies, is just one single bubble in an infinite, frothing sea of space. In such a boundless expanse, the arrangement of particles cannot be unique forever. Given an infinite amount of space and a finite number of ways particles can arrange themselves, every possible configuration must eventually repeat. This is a direct, almost inevitable consequence of the physics we already accept, born from the theory of cosmic inflation. This theory suggests that in the earliest moments after the Big Bang, space itself underwent a period of unimaginably rapid expansion, stretching far beyond what we can ever hope to see. Our entire observable universe is just one patch of this vastly larger and likely infinite whole. Think of it like a deck of cards. If you shuffle a deck a finite number of times, you will get a certain sequence of cards. But if you had an infinite number of decks and you shuffled all of them for all of eternity, every single possible ordering of the 52 cards would appear not just once, but an infinite number of times. Now replace the cards with every fundamental particle in the universe. In an infinite cosmos, the precise arrangement of particles that makes up you, your life, and your entire history is not a one-time event. It is a pattern that must be repeated with near-perfect fidelity and unimaginable distance away. there is another version of you reading this exact sentence right now. Another where you made a different choice years ago that led to a completely different life, and another where Earth never formed at all. These are not ghostly echoes or spiritual doubles. They are concrete, physical universes governed by the same laws of physics, existing in regions of space so vastly distant that light from them will never reach us. The implications are staggering. Every event that is remotely possible, no matter how unlikely, has not only happened somewhere but is happening an infinite number of times. This forces us to confront a profound question about our own place in the cosmos. Are we truly unique, or are we simply one iteration of a pattern written into the fabric of an infinite reality? Yet even this infinite tapestry of identical bubbles is only the first level of a much grander structure. The Level 2 multiverse proposes that our entire cosmic expanse, with its specific laws of physics, is just one isolated pocket in a frothing, eternal sea of creation. Here, the laws of nature themselves are not universal constants but local ordinances, changing from one bubble universe to the next. This breathtaking vision emerges from the theory of eternal inflation. Picture the primordial vacuum of space not as empty nothingness but as an unstable, energetic field. Like a pot of water boiling endlessly, this field continuously spawns new regions where inflation stops. Each of these regions becomes its own separate Big Bang, its own pocket universe, forever disconnected from our own. Within each of these newborn bubbles, the fundamental forces and constants are randomly set. In one, gravity might be overwhelmingly strong, causing universes to collapse instantly back into nothing. In another, the nuclear forces might be too weak to ever bind protons and neutrons into atoms, preventing stars or planets from ever forming. Our universe seems curiously fine-tuned for life. The strength of gravity, the mass of an electron, the force that holds atomic nuclei together. If any of these values were even slightly different, complex structures, and therefore life would be impossible. In the Level 2 multiverse, this fine-tuning is not a miracle. It is a simple consequence of probability. We can only exist in one of the rare, hospitable bubbles where the numbers just happen to fall into the narrow range that allows for galaxies, planets, and conscious observers. We find ourselves in a universe that permits our existence, but we are surrounded by an unimaginable plurality of dead, sterile, or wildly alien realities where physics follows a completely different and inhospitable script. This transforms our cosmic address from a single universe to one neighborhood in an infinite metropolis of physical laws. But the branching of reality does not stop at the boundaries of separate cosmic bubbles. It may be happening right here, right now, with every single quantum event. This is the many worlds interpretation, a theory that takes the multiverse from the cosmic scale down to the personal, suggesting that our reality is constantly splitting into countless new versions of itself. The roots of this idea lie in the strange, counterintuitive world of quantum mechanics. For decades, the dominant view was the Copenhagen interpretation, which states that a quantum particle, like an electron, exists in a blurry cloud of all possible states, called a superposition, until it is observed. At the moment of observation, this cloud of possibilities collapses into one single, definite reality. The act of looking, according to this view, forces the universe to make a choice. The many worlds interpretation rejects this special role for the observer. It proposes that the superposition never collapses. Instead, every possible outcome of a quantum event does happen, but each one plays out in a newly branched parallel universe. The classic thought experiment of Schrödinger's cat makes this starkly clear. A cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers and the cat dies. If it does not decay, the cat lives. According to Copenhagen, until someone opens the box, the atom is in a superposition of both decayed and not decayed, and the cat is simultaneously alive and dead, a ghostly mix of states. The many worlds view offers a different yet equally startling resolution. When the box is sealed and the quantum event occurs, the universe splits in two. In one universe, the atom decays and the cat dies. In the other, the atom does not decay and the cat lives. Both outcomes are equally real. There is no superposition, only a continual division of reality into every possible timeline. This means that for every quantum choice, for every random event at the subatomic level, a new universe is created. Every time you flip a coin, there is a universe where it lands heads and another where it lands tails. In one world, you took the job you were offered. In another, you turned it down. All versions are real, playing out in a vast, ever-expanding tree of alternate histories. The philosophical weight of this is immense. It suggests that every regret, every near miss, and every road not taken is in fact a path that was taken by another version of you. It removes chance from the equation, replacing it with absolute determinism across an infinite ensemble of worlds. Are we merely walking one branch of an infinite tree, forever unaware of the other versions of ourselves, living out the consequences of every possible decision? While the many worlds interpretation divides reality into countless branching paths, another theory proposes that the very substance of reality is woven from threads far stranger than particles. String theory suggests that the most fundamental ingredients of the universe are not tiny, zero-dimensional dots, but unimaginably small, vibrating loops of energy. Think of the strings on a violin. A single string can vibrate at different frequencies, producing a wide range of distinct notes from a low C to a high G. In string theory, each elementary particle is akin to a different musical note. The specific vibration pattern of a string determines whether it manifests as an electron, a quark, or a photon. One resonance creates the building blocks of matter, while another creates the force carriers that glue the cosmos together. In this elegant framework, the entire universe is a cosmic symphony composed of these tiny, oscillating strings. For this beautiful mathematical symphony to work, however, the strings require a stage with more dimensions than we can perceive. The theory is only consistent if space-time has not just the 3 spatial dimensions we know, but a total of 10 or even 11 dimensions. So where are these extra dimensions? The leading idea is that they are compactified or curled up into shapes so incredibly tiny on the scale of the strings themselves that they are completely hidden from our view. A simple analogy is a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl on its surface, you would discover it has a second dimension, curled into a small circle all the way around. Our reality may be similar. We freely move through the 3 large, familiar dimensions, while 6 or 7 others are coiled into intricate, microscopic shapes at every single point in space. The specific geometry of these hidden dimensions would dictate the resonant patterns of the strings, which in turn would set the laws of physics for our entire universe, determining the strength of gravity and the mass of an electron. This transforms the cosmos into a structure of profound depth, with the most fundamental rules of existence written in the secret, folded geometry of dimensions we cannot see. The elegant strings of this cosmic symphony may be merely the shadows of something far grander. M-theory takes the concepts of string theory and elevates them to an even more profound level, suggesting that the fundamental one-dimensional strings are actually just slices of much more complex, higher-dimensional objects. These entities are known as branes, short for membranes. A one-dimensional string is a one brane. A two-dimensional sheet or membrane is a two-brane. This logic extends upwards, proposing that our entire 3-dimensional universe could be a single, vast 3-brane floating within a higher dimensional space called the bulk. This is not just a small adjustment to the theory. It is a complete reimagining of our cosmic home, transforming it from a solitary stage into one island in a much larger hidden ocean. The bulk is the true higher dimensional arena, and our brain is a dimensional slice within it, trapping all the particles and forces we know except for one. This single exception could solve one of physics' oldest puzzles. Gravity feels incredibly weak compared to the other fundamental forces. A small refrigerator magnet can overcome the gravitational pull of the entire Earth, lifting a paperclip with ease. Why is gravity so feeble? The brain world scenario offers a stunning explanation. It proposes that the particles of matter and the carriers of the electromagnetic and nuclear forces are like ink stains trapped on the surface of a page. They are stuck to our brain, unable to leave. Gravity, however, is different. It is a manifestation of the geometry of space-time itself. In this model, gravity is not confined to our brain. It can leak, it can seep out into the bulk, spreading its influence across all the extra dimensions. Imagine our universe as a water-soaked sponge sitting on a laboratory table. The water represents all the familiar forces and matter confined entirely within the sponge, but a little bit of heat representing gravity radiates out from the sponge into the entire room. The heat dissipates, becoming weaker from the perspective of someone focused only on the sponge. In the same way, the true strength of gravity is diluted because it spreads out into the unseen bulk, leaving only a faint shadow of its power within our brain. This single idea elegantly accounts for gravity's puzzling weakness without inventing any new particles or forces. It simply recontextualizes our reality, suggesting we are experiencing only a fraction of a force whose full power resonates across dimensions we cannot access. What other cosmic forces might be spilling out from our island universe into the vast, dark ocean of the bulk? This notion of our universe as a solitary brain adrift in a higher dimensional bulk leads to a radical alternative to the Big Bang. The ekpyrotic universe theory proposes that our cosmic genesis was not a singular explosion from an infinitely dense point, but a violent, transformative collision between two of these vast, multidimensional membranes. Picture two immense parallel sheets of reality floating silently in the dark expanse of the bulk. Over eons, they draw closer, pulled by a force across the extra dimensions. They do not simply touch, they slam together. The incredible energy of this impact spread across the entire surface of our brain did not create matter and energy from nothing. It ignited it, heating the cold, empty brain to an unimaginable temperature and setting off the expansion and evolution we now call the Big Bang. In this scenario, the Big Bang was not the absolute beginning of time and space, but a catastrophic event within a pre-existing, higher dimensional reality. This elegantly sidesteps one of the most vexing problems in cosmology, the initial singularity. The idea of a point of infinite density and temperature, where the known laws of physics completely break down, is replaced by a powerful yet physically plausible collision. The theory grows even more profound when extended into a cyclic model. After the collision, the two brains rebound and fly apart, beginning the expansion that defines our universe today. But the attractive force between them remains. Eventually, the expansion of our brain will slow, halt, and reverse. The brains will be drawn together once more across the vastness of the bulk for another cataclysmic encounter. In this grand vision, the universe has no true beginning and no final end. It is an endless cycle of creation and destruction, a cosmic heartbeat echoing across the hidden dimensions. Each collision resets the cosmic clock, birthing a new universe from the ashes of the old, with the energy of each crash fueling the next expansion. This transforms our entire cosmological history into a single chapter in an infinite volume saga, raising a haunting possibility. If this cycle is eternal, then every configuration of matter and energy must recur. Every life you have lived and every possible variation of it has happened countless times before and will happen again in an endless, deterministic loop across the breadth of eternity. Are we living through just one iteration of a story that has been told and will be told forever? the endless cosmic cycle of colliding branes presents a universe of immense, almost unimaginable scale. Yet this entire grand structure, from the smallest vibrating string to the vastness of the cyclic multiverse, could be nothing more than an intricate fabrication. The simulation hypothesis proposes that our reality is not base reality at all, but an artificial construct, a sophisticated simulation running on the computer of a civilization so advanced their technology would be indistinguishable from magic. This idea moves from pure philosophy into a startling statistical argument, most famously framed by Nick Bostrom. He presents a trilemma, a set of three possibilities, one of which must almost certainly be true. First, almost all civilizations at our level of development go extinct before they can create realistic simulations. Second, any civilization that reaches that technological peak has no interest in running such simulations. Or third, we are almost certainly living inside one. If even a single advanced civilization avoids extinction and develops a curiosity about its own past or the nature of existence, it might choose to run vast numbers of ancestor simulations. The number of simulated minds in such a scenario would astronomically outnumber the one set of original biological minds. Therefore, if such simulations are possible, it is statistically far more likely that we are among the simulated beings than the original ones. Beyond the philosophical argument, some scientists point to potential glitches in the matrix, features of our universe that resemble the hallmarks of a computed reality. Just as a digital image, when zoomed in too far, reveals its underlying pixelated grid, space-time itself may have a fundamental resolution limit. The Planck length is the smallest possible measurable unit of distance in the universe. You cannot measure anything smaller than this, not because of our technological limitations, but because physics itself seems to break down. This is exactly what you would expect if the universe were rendered on a cosmic computer with a finite processing power, a pixel size for reality. Furthermore, the laws of physics appear to operate with a set of rules and constants, much like the source code of a video game. The speed of light acts as an ultimate processing speed limit. Quantum mechanics, with its probabilities and discrete energy levels, behaves remarkably like a system optimizing its computational resources, only calculating the precise state of a particle when it is being observed. Why does the universe seem to run on mathematics? Because the simulation is, at its core, a mathematical model. This perspective reframes our entire existence. The stars are not distant fusion reactors, but meticulously rendered points of light. The ground beneath your feet is not solid matter, but a supremely convincing data stream. Your very consciousness could be a sophisticated algorithm experiencing a pre-written narrative. If this is true, then the deepest laws of physics we strive to uncover are not the laws of nature, but the operational parameters of the machine we are running on. What does that make our search for meaning if our reality is just another layer of code in a universe we can never truly see? Cosmic inflation was a sudden and violent growth spurt for the universe. In the first fleeting fraction of a second after its birth, space itself expanded faster than the speed of light, stretching a subatomic speck of primordial energy into a cosmos of staggering size. This explosive beginning explains why our universe is so uniform, so flat, and so large. But the mechanism that drove this inflation may never have completely turned off. Instead, it might be a perpetual feature of the vacuum of space, an engine of eternal creation. Think of the universe not as a single, expanding balloon, but as an endlessly rising loaf of raisin bread. The dough represents the inflating energy of space. Most of the dough is still expanding, stretching the distances between raisins at an incredible rate. But in certain spots, raisins can become bubbles. In these localized regions, the inflationary energy decays, converting into the hot soup of particles and radiation that makes up a stable universe like our own. Each of these bubbles is a separate pocket universe, forever isolated from the others by the ever-expanding walls of inflating space. This is the inflationary landscape, a vast and frothing multiverse where the process of cosmic birth is ongoing. The properties of each bubble are not identical. The specific way the inflationary energy decays in a given region can randomly set the values of the fundamental constants. The strength of gravity, the mass of electrons, even the number of spatial dimensions could be locked into place with a different set of numbers in each new bubble. Our entire cosmos, with its hundreds of billions of galaxies, is just one bubble among an infinite number, a single habitat in a cosmic archipelago where the very laws of physics are local. We find ourselves in a bubble where the constants allow for atoms, stars, and life, not because it was destined, but because it was possible. An infinite number of other bubbles are stillborn, their physics too hostile for any structure to form. This landscape transforms the mystery of our universe's apparent fine-tuning from a cosmic coincidence into a simple question of real estate. We could only ever emerge in a bubble that could support us, even if such bubbles are incredibly rare in the grand scheme of things. The universe is not just vast in space, but in possibility, a tapestry of physical law where every conceivable rule set is written somewhere in the inflationary foam. Our persistent failure to detect dark matter might be a simple matter of perspective. We have been searching for a ghost in our own house when it could be the echo of a neighbor's life next door. This leads to a theory that reframes one of cosmology's greatest puzzles. Dark matter, the invisible substance that binds galaxies together, may not be a strange, unknown particle at all. It could simply be the ordinary matter of a parallel universe, a world separated from ours by a hidden dimensional gap. Recall the brane world scenario, where our three-dimensional universe is a membrane floating in a higher dimensional bulk. Now imagine another brane, a parallel reality, hovering just a fraction of a millimeter away in an extra, coiled-up dimension. For the inhabitants of that universe, their world is just as solid and real as ours. Their stars shine, their planets form, and their physicists might be just as perplexed by the unexplained gravitational pull they detect from our own brain. The matter in that parallel world is completely ordinary to them, made of protons, neutrons, and electrons, but to us it is utterly dark and undetectable. This is because all the forces that allow us to see and touch are trapped on our respective brains. The particles of light, the forces of electromagnetism and nuclear interactions are like actors confined to their own stages. They cannot jump the gap to the other brain. Gravity, however, is the exception. As the manifestation of space-time itself, it is not bound to any single brain. It can leak across the dimensional divide. The gravity generated by the stars and planets in that parallel universe bleeds through into our own. We feel its pull, we measure its profound influence on the rotation of our galaxies and the bending of light from distant stars, but we cannot see its source. It is as if we are living in one room of a vast house, and we can feel the floorboards vibrate from the footsteps of someone walking in the room next to ours. We know something massive is there, something that exerts a real force on our environment, yet the wall between us prevents us from ever seeing who or what is causing it. In this elegant explanation, the search for dark matter transforms. We are not hunting for a single, elusive particle. We are sensing the collective gravitational shadow of an entire other cosmos, a silent, invisible twin to our own, forever separated by a thin veil of higher dimensional space. The mystery of the missing mass becomes a question of cosmic architecture, hinting that the emptiness around us is not empty at all, but filled with the ghostly presence of another reality. The ghostly pull of a parallel universe could explain dark matter, but an even more dominant force is actively tearing the cosmos apart. Dark energy is the name for this mysterious pressure, a repulsive force that counteracts gravity on the largest scales, driving the expansion of the universe to accelerate. Its discovery in the late 1990s was a profound shock, revealing that the cosmic destiny is not a slow coast or eventual collapse, but a runaway expansion into ever colder isolation. The leading candidate for this bizarre energy is something born from the very fabric of emptiness. It is the cosmological constant, the energy intrinsic to the vacuum of space itself. Think of empty space not as a true void, but as a seething quantum foam. At the tiniest scales, virtual particles constantly blink in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This ceaseless activity should imbue every cubic centimeter of space with a certain energy density, a background hum of existence that exerts a gentle, negative pressure pushing space apart. This is the cosmological constant, a concept first proposed by Einstein and later abandoned as his greatest blunder. It now appears he may have been right for the wrong reasons. The problem is one of catastrophic scale. When physicists attempt to calculate the expected value of this vacuum energy from quantum theory, the number they get is absurd. It is too large by a factor of 1 followed by 120 zeros. This is not just a small error, it is the most spectacular failure of a theoretical prediction in the entire history of science. Our universe's actual, observed cosmological constant is unimaginably tiny, but not zero. This staggering discrepancy is known as the vacuum catastrophe, and it points to a fundamental gap in our understanding. How can the predicted energy of the vacuum be so immense, while the effect we measure is so infinitesimally small? The inflationary multiverse may offer a way out of this crisis. In that endless landscape of bubble universes, the value of the cosmological constant is not a fixed law. It is set randomly in each pocket during its formation. The vast majority of these bubbles would have a cosmological constant so large that space would rip itself to shreds instantly, preventing any structure from ever forming. A tiny fraction, by pure chance, would have a constant as small as ours or even zero. We, of course, find ourselves in one of those rare habitable pockets where the numbers allow for galaxies to coalesce and life to ponder the mystery. Our universe is not fine-tuned. It is simply one of the very few addresses in the multiverse where the rent is low enough for existence to take root. This transforms the worst prediction in physics from a paradox into a selection effect, a quiet clue that our reality is just one possibility in an infinite array of failed experiments. The smooth expansion of space-time predicted by Einstein's equations shatters completely at the edge of a black hole. Here, in the warped space surrounding these cosmic monsters, we find a paradox so profound it threatens to unravel our entire understanding of physics. The black hole information paradox pits the two pillars of modern physics, general relativity and quantum mechanics, against each other in a battle with no easy resolution. It all began with Stephen Hawking's stunning realization that black holes are not truly black. Due to weird quantum effects occurring right at the precipice of the event horizon, black holes must slowly leak radiation. They evaporate, fading away over astronomical timescales. This Hawking radiation, however, presents a catastrophic problem. The radiation is purely thermal, a featureless glow that carries no information about what fell in. It is like burning a book and claiming that the unique arrangement of its words is preserved only in the heat and light of the fire. According to the unwavering rules of quantum mechanics, information can never be truly lost. The history of every particle, its properties and its relationships must be preserved in some form forever. If a book falls into a black hole and the black hole evaporates, leaving behind only this random thermal radiation, then the information within that book is gone forever. The universe would have no memory of its contents, violating a fundamental quantum law. This is the paradox. General relativity, with its smooth, predictable space-time, says that information crosses the event horizon and is crushed into the singularity, effectively gone from our universe. Quantum mechanics insists the information must be preserved. Both cannot be right. One potential solution brings us back to the holographic principle. It suggests that the information of everything that falls into the black hole is not lost inside. Instead, it is meticulously encoded in a scrambled quantum form on the two-dimensional surface of the event horizon. The three-dimensional interior of the black hole is an illusion, a projection of this data. As the black hole evaporates via Hawking radiation, this surface information is slowly and faithfully released back into the universe, preserving the cosmic ledger. Another, more violent resolution is the black hole firewall. This theory proposes that the event horizon is not a smooth gateway but a searing wall of energy. The moment an object crosses the point of no return, it is not gently stretched by tidal forces. It is instantly incinerated. This firewall would destroy the object, but in doing so, it would convert its information into energy, preserving it in the Hawking radiation. The cost, however, is immense. It means that the smooth fabric of space-time, a cornerstone of general relativity, abruptly ends in a curtain of fire. Both ideas are deeply strange, forcing us to choose between a universe that is fundamentally holographic or one that is brutally destructive at its most extreme boundaries. The fate of information, and perhaps the consistency of reality itself, hangs in the balance. If black holes are cosmic prisons from which nothing escapes, then their theoretical opposites are fountains of pure creation. White holes are the hypothetical time-reversed twins of black holes, regions of space-time where matter and energy can only pour out, with nothing ever able to enter. While a black hole's event horizon is a one-way street inward, a white hole's boundary is an exit door that cannot be opened from the outside. The mathematics of general relativity allows for such an object, a place where the universe is perpetually giving, yet forever closed to visitors. Imagine a waterfall running in reverse, its water defying gravity to surge upward from the pool below. A white hole would be a similar violation of our cosmic intuition, a singularity that endlessly expels the very stuff of reality. The catch is that white holes are profoundly unstable according to our current understanding. Any single particle of dust falling onto one would be enough to collapse its delicate structure, potentially triggering its transformation into a black hole. This fragility means that if they ever did form in the early, violent universe, they likely blinked out of existence almost instantly. Yet their theoretical existence opens a door to an even more thrilling possibility. When the equations for a black hole and a white hole are stitched together, they can form a tunnel through the fabric of space-time itself. This is the Einstein-Rosen bridge, more popularly known as a wormhole. Picture the universe as a vast, flat sheet of paper. To get from a point on one side to a point on the other, you would normally have to travel the long way across the entire surface. But if you could fold the paper so the 2 points touch, a wormhole would be a tiny bridge connecting them, a shortcut through the higher dimension that the paper is lying in. This tunnel would link 2 distant regions of space, or perhaps even 2 completely separate universes, allowing for travel that would otherwise be impossible. The challenges, however, are as immense as the promise. First, the entrance to a traversable wormhole would likely be a black hole, presenting the obvious problem of surviving the crushing gravity and tidal forces. Second, the throat of the wormhole, the tunnel itself, would be held open by a form of matter with negative energy density, something we have only ever seen in tiny, quantum-sized effects. To stabilize a wormhole large enough for a person to pass through, you would need a planet's worth of this exotic material, a substance that effectively generates anti-gravity to keep the tunnel from pinching shut instantly. Even if such a feat were possible, the wormhole could still be a one-way trip or a gateway to an unknown destination. A wormhole connecting 2 points in our own universe could serve as a time machine if one end were moved at relativistic speeds, while one linked to a white hole in another brane could be a passage to a parallel reality with entirely different physical laws. These cosmic shortcuts remain firmly in the realm of theory, but they ignite our deepest dreams of exploration, offering a vision of a universe so deeply connected that its farthest reaches are just a step away. This fine-tuning of the universe is not a minor detail but a profound condition for our existence, leading directly to the anthropic principle. It is a simple, almost tautological idea with staggering implications. The weak anthropic principle states that we should not be surprised to observe a universe with constants perfectly suited for life, because if those constants were any different, we would not be here to observe anything at all. We are, in essence, cosmic selectors, unavoidably biased to find ourselves in a habitable niche. It is like a puddle marveling at how perfectly the hole it sits in matches its own shape, without considering that the hole is the only reason the puddle exists at all. This is not an explanation for why the universe is this way, but a logical filter for our observations. The strong anthropic principle takes a much more provocative stance. It argues that the universe must, in some fundamental sense, have properties that allow life and consciousness to emerge. This version suggests a deeper teleology, a universe that seems almost designed with observers as a necessary outcome. This is where the principle powerfully intersects with the multiverse. If there is only one universe, its improbable fine-tuning seems to demand an explanation, perhaps even a designer. But if the multiverse is real, the mystery evaporates. In an infinite landscape of bubble universes, each with randomly dialed physical constants, the vast majority are sterile voids. A tiny fraction, by pure chance, have the right numbers for stars, planets, and life. We do not live in a special universe, we live in a survivable one. Our existence is the result of a cosmic lottery we could not help but win, simply because the losing tickets are universes of nothingness, with no one to complain about their bad luck. The anthropic principle transforms our perspective from asking why the universe is fit for life to asking what other forms of reality are possible in the silent, dark majority of the cosmos. While string theory adds extra dimensions to reality, a rival idea takes the opposite approach. Loop quantum gravity seeks to rewrite the laws of physics by breaking space itself into its most fundamental pieces. It proposes that the smooth, continuous space-time described by Einstein is an illusion, a large-scale approximation of a reality woven from a billion tiny, indivisible loops. Picture the fabric of the cosmos not as a blank, featureless sheet, but as an incredibly fine mesh. Each interlocking loop in this network is a single quantum of space, a stitch in the tapestry of reality. These loops connect to form a dynamic, vibrating structure known as a spin foam, a seething, frothing substrate where space and time are born from their interactions. This is a universe built from pure relationship, where geometry is not a background stage but the main actor. The most profound consequence of this granular space is the complete eradication of singularities. In Einstein's general relativity, the center of a black hole and the beginning of the Big Bang are points of infinite density, where the laws of physics simply break down and our equations scream in protest. But in loop quantum gravity, you cannot compress matter and energy into an infinitely small point because space itself is not infinitely divisible. There is a smallest possible size, a fundamental pixel of reality. When matter is crushed to this ultimate density, it meets a wall of pure repulsive force generated by the quantum nature of space. This leads to a breathtaking alternative to the cosmic origin story. The Big Bang was not the absolute beginning. Instead, it was a great rebound. A previous universe, perhaps similar to our own, collapsed under its own gravity. But instead of crushing itself into nothingness, it reached this maximum density and bounced. The immense repulsive force of quantum space-time hurled everything outward, creating the expanding universe we observe today. Our entire cosmic history could be one chapter in an endless cycle of contraction and expansion, a cosmic heartbeat driven by the discrete nature of space itself. This theory reveals a hidden layer of reality that is digital at its core, a universe where not just matter but the very void it sits in is quantized. What would it mean to perceive this granular foundation underlying every seemingly smooth surface we touch? This granular, pixelated view of space-time is not the only path to quantum gravity. Another powerful idea rebuilds the cosmos from the ground up, using the simplest of geometric tools. Causal dynamical triangulations constructs the entire history of the universe from a vast collection of tiny, four-dimensional building blocks. Imagine giving a powerful computer a near-infinite supply of microscopic, higher-dimensional triangles and tetrahedrons, the geometric pieces of a four-dimensional puzzle. The rules are simple. The pieces must fit together smoothly, and every step in the construction must respect a strict sequence of cause and effect. There are no pre-existing dimensions or a background stage. The computer then connects these pieces at random, following the rules, building every possible configuration of this elemental spacetime. What emerges from this digital primordial soup is a revelation. Out of the initial chaos of jumbled shapes, a smooth, classical universe spontaneously crystallizes. The random connections and folds do not produce a tangled mess. Instead, they self-organize, giving rise to the four-dimensional spacetime we recognize, complete with its 3 dimensions of space and 1 of time. This is not a feature programmed into the model. It is a phase transition, an emergent property, much like liquid water freezing into structured ice. The model reveals a hidden layer of profound simplicity beneath the apparent complexity of our world. The vast, expanding cosmos, with its galaxies and nebulae, may be the large-scale expression of a fundamental reality built from an unimaginable number of tiny, geometric events, each one a simple decision in a cosmic chain of cause and effect. This suggests that the dimension of time itself is not an illusion, but a necessary ingredient for a stable reality to emerge from the quantum fog. Without the rigid enforcement of causality, the model collapses back into a formless, higher-dimensional foam. We perceive a continuous flow of time because our reality is one specific, stable configuration in a vast ensemble of possible computational histories. The universe is not happening on a stage. It is the stage, perpetually assembling itself one causal connection at a time. Our most basic assumptions about how particles interact may be built on an illusion. The amplituhedron is a geometric shape of such stunning beauty and simplicity that it threatens to upend our entire understanding of quantum events. For decades, calculating how subatomic particles scatter off one another has been an excruciatingly complex task. Physicists had to account for every possible path and interaction, a process involving thousands of intricate mathematical terms in massive equations that could take weeks or months to solve. The amplituhedron reduces this monumental computational nightmare to a single, elegant question. What is the volume of this multidimensional shape? The answer to that simple geometric puzzle directly gives you the probability of how particles will interact. It is as if you replaced a 1,000-page instruction manual for building a house with a single, perfect blueprint. This discovery suggests that the messy, complicated quantum world we calculate is merely a shadow projected from a far cleaner, more fundamental geometric reality. This new geometry forces us to abandon 2 sacred pillars of physics, locality and unitarity. Locality is the common-sense idea that objects can only be influenced by their immediate surroundings, not by distant events. Unitarity is the guarantee that the probabilities of all possible outcomes of any interaction must always add up to 100%. These principles are the bedrock of our quantum theories. Yet the amplituhedron shows they are not fundamental. They do not exist within its pristine geometric form. Instead, they emerge only when we translate the shape's volume back into the language of particles and forces. This is a radical shift in perspective. The universe is not built from tiny billiard balls bumping into each other in a local neighborhood. What we perceive as a cause and effect interaction between two particles could be a manifestation of a single, unified geometric truth. The particles themselves may not be taking individual paths through space and time. The entire history of their interaction might be encoded all at once in the timeless structure of the amplituhedron. Space-time itself, the stage for all events, may simply be a derived concept, a useful tool that falls out of this deeper, more beautiful mathematics. What other fundamental aspects of our reality are merely emergent shadows, waiting for a new geometry to reveal their true, hidden form? This strange thought experiment pushes the logic of probability to its absolute breaking point. The Boltzmann brane paradox asks a deeply unsettling question. Could your mind, your memories, and your entire perception of reality be nothing more than a fleeting, random accident? The idea emerges from the second law of thermodynamics, which states that the universe naturally progresses from order to disorder. Yet, statistical physics also allows for the opposite. In any system, there is always a tiny, non-zero probability for a random fluctuation to create order from chaos. In a truly eternal and vast universe, even the most improbable events are not just possible, they are inevitable. Given enough time, a fully formed, self-aware brain could simply pop into existence out of the void. This brain would not be attached to a body, it would not have a past. It would simply appear, complete with a lifetime of fabricated memories, convinced it is a person living in a real world, thinking its own thoughts. According to this logic, in an eternal cosmos, the number of these disembodied, self-aware fluctuations should vastly outnumber the number of brains that formed through the slow, arduous process of evolution in a stable universe like ours. You are far more likely to be a random Boltzmann brain, hallucinating a coherent reality for a single moment before dissolving back into chaos, than you are to be a real, biologically evolved person. This is not just a philosophical curiosity, it is a direct challenge to our best cosmological models. If our theory of the universe predicts that most conscious observers are these random fluctuations, then the theory is likely flawed. A good model of reality should not imply that our own orderly experiences are statistically impossible. The paradox forces physicists to seek models of the cosmos that avoid an eternal, static future, perhaps one with a definite end or a continuous evolution that makes such random aberrations infinitely unlikely. It serves as a cosmic sanity check, testing whether our understanding of the universe is consistent with our own existence as coherent, enduring observers. Your certainty that you have a body, a history, and a future could itself be the most convincing illusion of all. The very fabric of reality might be a language we invented. The mathematical universe hypothesis takes this idea to its ultimate conclusion, arguing that our physical world is not merely described by mathematics, but that it literally is a mathematical structure. According to physicist Max Tegmark, we are not discovering mathematical laws that govern an independent reality. We are discovering that we are living inside the math itself. Your consciousness, the stars, the flow of time, all of it could be a specific, self-consistent mathematical pattern experiencing itself from within. This is the ultimate form of reductionism, peeling back every layer of physics until only the abstract relationships of numbers and geometry remain. Tegmark organizes this staggering vision into a four-level multiverse, each level more profound than the last. The first level is the infinite cosmic foam we already explored, where distant regions of space contain copies of you. The second is the inflationary landscape, where different bubble universes have different physical constants. The third is the many worlds of quantum mechanics, where every possible outcome branches into a new reality. But the fourth level is the final step, the ultimate ensemble. It states that every single mathematical structure that is logically consistent exists as a physical reality. Think of mathematics as a vast library. Our universe, with its 3 dimensions of space and 1 of time, governed by the specific equations of general relativity and quantum field theory, is just one book on an infinite shelf. Other books describe universes with 10 dimensions, or with no time at all, or where the concept of number is entirely different. If a set of axioms and rules is free from internal contradiction, then that universe is real. In one mathematical structure, the laws might be simple Euclidean geometry, and the inhabitants could be sentient triangles living on an infinite plane. In another, the structure could be so alien that words like particle, force, or even existence have no meaning we could comprehend. This hypothesis dissolves the ancient mystery of why mathematics is so unreasonably effective at describing the natural world. It is not effective, it is fundamental. The universe is mathematical down to its very core because there is nothing else for it to be. The matter we are made of, the forces that hold us together, are merely representations of an underlying, immutable mathematical truth. We are patterns of information in a cosmic computation that has been running since the beginning of logical time. The elegant symmetries of mathematics might be whispering a profound secret about the particles that build our world. Supersymmetry is a theory proposing a deep, hidden relationship between the 2 fundamental classes of particles, the force carriers and the matter particles. It suggests that for every known particle in the universe, there exists a hidden, super-heavy twin, a superpartner waiting to be discovered. This is not just a minor addition to the particle family. It is a radical doubling of reality at its most fundamental scale. On one side, you have the fermions. These are the building blocks of matter, the particles like electrons and quarks that come together to form everything you can touch, from the ground beneath your feet to the stars in the sky. They are the ultimate individualists, obeying a rule that prevents them from occupying the same quantum state. On the other side are the bosons. These are the messengers of the forces, particles like photons that carry light and gluons that bind atomic nuclei. They are social particles, happy to pile on top of one another, which is how they create coherent force fields. Supersymmetry proposes a fundamental bridge between these 2 distinct worlds. It states that for every fermion, there should be a bosonic superpartner. An electron would have a partner called a selectron. A quark would have a squark. Conversely, for every boson, there should be a fermionic partner. The photon would have a photino, and the gluon would have a gluino. This elegant symmetry solves one of the most stubborn problems in modern physics, known as the hierarchy problem. The question is simple yet devastating. Why is gravity so unimaginably weaker than the other fundamental forces? The math of our current best model, the Standard Model, suggests that the quantum jitters of virtual particles should drive the mass of the Higgs boson, and by extension the scale of the weak nuclear force, up to a level quadrillions of times higher than what we actually observe. It is like a pencil balanced perfectly on its tip for billions of years in a hurricane. It makes no sense. Supersymmetry provides a stunningly graceful solution. The contributions from ordinary particles and their super-heavy superpartners would be equal in magnitude but opposite in sign. They would cancel each other out with perfect precision, leaving the Higgs mass delicately fine-tuned and stable, just as we observe. This cancellation is not a convenient fix. It is a natural mathematical consequence of the symmetry itself. Furthermore, the lightest of these superpartners becomes a perfect candidate for the identity of dark matter. This particle would be stable, electrically neutral, and would only interact through gravity and the weak nuclear force, exactly matching the profile of the invisible matter that holds galaxies together. It would be a relic from the early universe, a frozen shadow of the symmetric state that existed when the cosmos was young and hot. Finding evidence for supersymmetry would be like discovering that every person in the world has an identical twin they never knew about, a twin whose existence explains countless mysteries. It would reveal a layer of cosmic order so profound that it connects the very substance of matter to the forces that shape it, completing a picture of reality we have only ever seen in fragments. But this elegant symmetry is built upon a universe with fixed scales and familiar properties. What if there exists an entire hidden sector of reality that plays by completely different rules, a realm without any fixed scale at all? This is the speculative world of unparticle physics. It proposes a shadowy sector of the universe governed by a theory that is scale invariant. In our everyday world, scale matters profoundly. A grain of sand behaves very differently than a sand dune, and a single water molecule has properties distinct from an ocean wave. This is because the forces and masses in our standard model have specific scales. But in a scale-invariant theory, the laws of physics look exactly the same no matter what magnification you view them at. There is no inherent mass or energy scale that defines a typical particle. Out of this featureless, scale-free void, a new form of matter could emerge, something physicists call unparticles. These would not be particles as we know them. An electron or a quark has a very specific mass. When you observe it, it appears as a sharp, well-defined point. An unparticle would have no single mass. Instead, it would behave like a fuzzy, continuous cloud of possibility, a blend of many different mass states all at once. Its behavior would be strange and unfamiliar. If you were to try and measure its properties in a particle collision, it would not leave a clean, sharp signal in a detector. Instead, it would manifest as missing energy, a subtle imbalance where energy and momentum seem to simply vanish, carried away by this ghostly, scale-less entity. Discovering unparticles would be like realizing that the world of music is not just made of distinct notes, but also contains a form of sound that is a continuous, unchanging drone, present at every possible pitch simultaneously. It would reveal a hidden layer of reality that is smooth and continuous where our own is granular and discrete, a silent background hum to the universe's noisy symphony. The elegant symmetry of supersymmetry is not the only way reality could be hiding a twin. An even more radical idea suggests the cosmos possesses a perfect, invisible reflection. The mirror universe theory proposes that for every single particle in our world, there exists a mirror copy, a shadow particle that forms a complete, parallel reality operating right alongside our own. This mirror world would have its own mirror atoms, mirror stars, and even mirror galaxies, all made from these elusive counterparts. The crucial difference is how these two realms interact. In our universe, particles communicate through a full suite of forces. Electromagnetism makes light. The strong force binds nuclei, and the weak force governs radioactive decay. But in the mirror universe, these forces might be entirely separate. The mirror photons would be blind to our eyes, and their mirror electrons would be untouched by our magnets. The two worlds would be like ghostly ships passing in the night, occupying the same space yet forever unaware of each other. There is, however, one fundamental force that cannot be so easily divided. Gravity is the manifestation of space-time itself, the shape of the cosmic stage. It does not care which actors are on it. Both our matter and mirror matter would bend the fabric of space-time, and through this shared curvature, they can feel each other's presence. This single, slender thread of connection could unravel one of astronomy's greatest mysteries. We know that galaxies rotate so fast they should fling themselves apart, yet something invisible holds them together. We call this something dark matter. What if dark matter is not a strange, unknown particle, but simply the collective gravitational pull of the mirror stars and mirror planets in the parallel galaxy that perfectly overlaps our own? We are feeling the weight of a hidden cosmos, a reality that is completely transparent to our light and our instruments, but whose mass tugs on our stars and bends the light from distant quasars. This explains why our most sensitive detectors have found nothing. They are designed to catch particles that interact via the electromagnetic or nuclear forces. They are built to see our world's light, A mirror neutron would pass through a mile of lead as if it were empty space, because it only speaks the language of mirror-strong forces, a language our detectors are deaf to. We are surrounded by an entire universe of matter, a bustling, vibrant reality whose only whisper to us is the gentle, persistent pull of its gravity, a ghostly hand guiding the dance of the galaxies. Our stubborn sense that time flows in one direction might be the universe's most convincing illusion. The laws of physics at their most fundamental level do not care if time runs forward or backward. This symmetry suggests a profound hidden layer where cause and effect are not a one-way street. The Wheeler-Feynman absorber theory tackles this head-on with a radical rethinking of a simple phenomenon, light. When an electron jiggles, it emits electromagnetic radiation, a wave that travels outward into the future. Classical physics tells us this wave radiates away to infinity, never to return. But Wheeler and Feynman asked a different question. What if the entire universe is set up to absorb that wave perfectly? They proposed that the electron's outgoing wave travels forward to the end of time, where it is met by an advanced wave, a solution to the equations that travels backward in time from the cosmic future. This returning wave converges back on the electron at the exact moment it jiggled, providing the resistance that explains why it loses energy. In this breathtaking picture, every emission of light is a handshake across eternity, a transaction between the past and the future that requires the entire universe from beginning to end to be in place for a single particle to shine. This is not magic, it is a solution that treats time as a two-way street where effects can ripple backward just as easily as they flow forward. The transactional interpretation of quantum mechanics takes this idea of two-way time and applies it to the quantum realm, offering a startlingly concrete vision of how the future influences the past. In this view, a quantum event begins when a particle sends an alpha wave forward in time. This wave is a cloud of possibility, exploring every potential path. When this wave is detected or measured, the universe at that future point sends a confirmation wave backward in time. This confirmation wave, traveling in reverse, selectively reinforces the original alpha wave, and it is this handshake across time that collapses the probability cloud into a single, definite reality. Think of it like an echo that starts from the future and travels to the past, telling the event how it will turn out. The particle does not choose a path until it receives confirmation from its own future. This is retrocausality, where the future actively participates in shaping the present. It resolves the strangeness of quantum superposition, not by splitting worlds, but by weaving a single, consistent timeline where the beginning and the end are inextricably linked. Your observation of a particle now is what confirmed its state in the past. This challenges our deepest intuitions about reality, suggesting that the unchangeable past is still being written by the choices of the future, and that the arrow of time is merely the direction in which we experience this eternal, two-way conversation. The seamless integration of mind and cosmos might be the universe's deepest secret. Panpsychism proposes that consciousness is not an accidental byproduct of complex brain chemistry, but a fundamental and ubiquitous feature of reality, as basic as space, time, and matter. This theory suggests that some form of subjective experience exists all the way down to the most elementary particles. An electron might possess a faint, primitive spark of inner life, a single note of feeling in the cosmic symphony. This is not to say an electron thinks or wonders. Its experience would be unimaginably simple, perhaps just a bare, raw awareness of its own existence and environment. The idea directly confronts the hard problem of consciousness, which asks why and how physical processes in the brain give rise to subjective, first-person experience. Why does the firing of neurons feel like anything at all? Why are we not just philosophical zombies acting without any inner world? Science can describe the mechanics of thought, but it cannot explain the qualia, the redness of red, or the pain of a stubbed toe. Panpsychism offers an elegant, if startling, solution. Consciousness did not emerge at some point in evolution. It was always there, a property woven into the fabric of reality. In this view, complex consciousness, like our own, arises when these simple, fundamental conscious entities combine into intricate systems. The human brain does not generate consciousness from nothing. It organizes and complexifies these fundamental building blocks of awareness, much like individual pixels combine to form a rich, detailed image on a screen. This transforms our understanding of our place in the cosmos. We are not conscious beings in an unconscious universe. We are the universe becoming aware of itself, a localized knot of intensified experience in a field of pervasive mind. The philosophical weight of this is immense, suggesting a hidden layer of reality where matter and mind are two sides of the same coin, forever entwined in the dance of existence. These cosmic shortcuts and warp drives demand a material that defies the very foundation of physics. The null energy condition is a cornerstone of classical general relativity, a rule stating that the energy density of any normal matter, when measured by any observer, can never be negative. Think of the universe's energy budget like a bank account. For all known forms of matter and energy, the balance is always positive or at least zero. You cannot have less than nothing. This principle ensures that gravity always attracts, that space-time remains stable, and that cause and effect proceed in an orderly fashion. It is the cosmic guardrail that keeps reality from descending into chaos. Yet, to build a traversable wormhole or an Alcubierre warp drive, you need to shatter this rule. You need exotic matter. This is not merely a different element on the periodic table. Exotic matter is a hypothetical substance that possesses a negative energy density. It would not just be light, it would be lighter than nothing. Its gravitational effect would be repulsive, a form of anti-gravity that pushes space-time apart rather than pulling it together. To visualize this, picture a wormhole as a tunnel between two distant points. The immense gravitational pull from the mass of the tunnel's walls would cause it to collapse into a singularity instantly, pinching shut faster than light could travel through it. The only way to keep this tunnel open is to line its throat with a ring of this exotic matter. Its negative energy would generate a powerful repulsive force, acting like a cosmic support beam to push the walls of the wormhole outward, counteracting the natural tendency to collapse and creating a stable passage. The same principle applies to a warp drive. To bend space-time into a bubble that carries a ship at effective speeds faster than light, you need a shell of negative energy to warp the fabric of the cosmos in a way normal matter simply cannot. The problem is that this exotic matter, while mathematically possible within certain solutions of Einstein's equations, has never been observed. In fact, its existence seems to violate the very energy conditions that prevent time travel paradoxes and other logical nightmares. The quest for it pushes at the boundaries of known physics, suggesting that to truly master the hidden layers of space-time, we may need to discover an entirely new form of reality, one where the most fundamental rules we rely on are merely local ordinances in a much stranger cosmos. The same geometric magic that might create wormholes between stars could be stitching together the very fabric of space itself. The ER equals EPR conjecture is a breathtaking proposal that two of Einstein's most radical ideas are not just related, but are fundamentally the same phenomenon viewed from two different perspectives. It forges a deep, unexpected bridge between the physics of the very large and the very small. On one side, you have ER, the Einstein-Rosen bridge, which is the formal name for a wormhole, a tunnel through the geometry of space-time. On the other, you have EPR, named for Einstein, Podolsky, and Rosen, who first highlighted the bizarre phenomenon of quantum entanglement, which Einstein himself famously called spooky action at a distance. This conjecture boldly states that they are equivalent. An Einstein-Rosen bridge is an EPR pair. In other words, every pair of entangled particles, every spooky connection that defies our classical intuition, is not communicating faster than light through empty space. They are linked by a tiny, microscopic wormhole. Think of two coins that are always guaranteed to land on opposite sides, no matter how far apart you separate them. In our conventional view, this seems like magic, but if ER equals EPR is correct, there is no spooky action. The two coins are not separate objects sending signals. They are two ends of the same microscopic tunnel, a shortcut through the geometry of reality that makes their instantaneous correlation perfectly natural. This transforms our understanding of entanglement from a ghostly connection to a tangible, physical link, a stitch in the fabric of space-time itself. The implications of this single idea are universe-altering. If every entangled pair is connected by a Planck-scale wormhole, then the entire cosmos could be a vast, dynamic web of these quantum threads. The smooth, continuous space we perceive might be an emergent illusion, a collective pattern arising from an unimaginably complex network of entanglement. Space itself may not be the foundational stage. It could be the final product woven into existence by these fundamental quantum connections. This suggests that the hidden layer of reality is not made of tiny strings or loops, but of information and relationship. To create space, you first need to create entanglement. This profound link between geometry and information is perhaps the strongest clue we have that the universe is, at its heart, a unified computational structure, and we are only just beginning to read its source code. Our own cosmic home could be the interior of a colossal black hole. This theory proposes that the Big Bang was not the absolute beginning, but the violent birth of a new reality from the collapse of a star in a much larger parent universe. When a massive star exhausts its fuel, it collapses under its own gravity, compressing its immense mass into an infinitely dense point, a singularity, and forming an event horizon, the point of no return. The mathematics describing this collapse are strikingly similar to the equations for an expanding universe, but running in reverse. The inward rush of a collapsing star mathematically mirrors the outward expansion of the Big Bang. This leads to a staggering possibility. The singularity at the heart of a black hole might not be a dead end, but a gateway. As matter is crushed to an ultimate density, the extreme conditions could trigger a quantum bounce, a rebound that creates a new, expanding space-time, entirely disconnected from the universe that spawned it. Our entire universe, with all its galaxies and stars, could be this newly forged reality, existing within the event horizon of a black hole we can never see beyond. This transforms the cosmos into a cosmic fractal, an endless matryoshka doll of universes. Every black hole that forms in our universe could, in its deepest heart, contain an entire new cosmos, bubbling into existence with its own laws of physics and its own stars. And within those universes, new black holes form, each one potentially birthing another level of reality. We may be living inside a black hole that exists within a black hole in an infinite regress of creation. This idea elegantly sidesteps the problem of the initial singularity, replacing a single, inexplicable beginning with an endless cycle of cosmic rebirth. It suggests that universes are not born from nothing, but from the death of stars in other worlds, making every black hole not a tomb, but a womb for new existence. The fragmented reality we perceive could be a grand unfolding from a deeper, unified whole. Physicist David Bohm proposed a radical vision of the cosmos, suggesting that our tangible world of separate objects and events is merely the explicate order. This is the unfolded reality, the part of the universe that has been flattened out into the familiar sequence of space and time. But beneath this surface level of existence lies what Bohm called the implicate order, an enfolded, hidden dimension where everything is interconnected in a state of wholeness. In this deeper reality, the entire cosmos is woven together, with every location containing, in some sense, every other location. To understand this, think of a hologram. If you take a holographic film and shatter it into a dozen pieces, each fragment does not hold a twelfth of the overall image. Remarkably, each tiny shard still contains the entire intact image, albeit at a lower resolution. The whole is enfolded within every single part. Bohm argued that the universe operates on a similar principle. Every electron, every star, and every conscious thought is a unique unfolding from this implicate order, a temporary expression of the underlying totality. The apparent separation between you and the screen you are looking at, or between Earth and a distant galaxy, is an illusion of the explicate level. At the fundamental, implicate level, all of these things are deeply and inseparably connected. This is not a spiritual metaphor, but a physical proposal for how quantum weirdness, like entanglement, might work. When two particles are entangled, their connection does not need to span a vast distance in the explicate order. In the implicate order, they were never truly separate to begin with. They are two aspects of a single, deeper reality, momentarily unfolded into our perception as distinct entities. This vision transforms our understanding of the cosmos from a collection of independent things to a seamless, dynamic flow of enfoldment and unfoldment. The universe is not a machine made of parts, but a holographic projection of a unity so profound that the entire story of existence is written in full at every single point. This ancient solution to the dark matter puzzle has returned with new force. Primordial black holes are not born from dying stars. They are cosmic fossils, hypothetical remnants from the universe's first chaotic second, when immense density fluctuations could have caused pockets of space to directly collapse into black holes. These objects would have formed long before the first stars flickered on, and they could range in size from smaller than an atom to more massive than 1,000 suns. For decades, this idea was largely set aside, as observations seemed to rule out black holes as the primary constituent of dark matter. If they were too common, they would disrupt the delicate balance of star clusters and subtly distort the light from distant stars, effects we simply did not see. The search focused instead on hypothetical subatomic particles like WIMP, but decades of sensitive experiments have failed to find a single one. This persistent silence has forced physicists to take another, harder look at the primordial black hole. The constraints have not vanished, but our understanding of them has evolved. We now know that a specific window of possibility remains open. Primordial black holes with masses comparable to a large asteroid or even a planet could potentially account for all the dark matter in the universe without contradicting any existing observations. These ancient black holes would be perfect dark matter candidates. They do not emit any light, they interact only through gravity, and they would be scattered throughout the galactic halo, their collective mass providing the invisible gravitational glue that holds galaxies together. Imagine our Milky Way galaxy not just as a swirl of stars, but as a sphere teeming with a billion silent, dark moons, each one a tiny, dense knot of space-time left over from the primordial fire. They would drift unseen between the stars, their gravitational presence the only evidence of their existence, a hidden layer of ancient architecture governing the grand design of every galaxy we see. The recent detection of gravitational waves from merging black holes by LIGO has reignited this theory, as some of those black holes were curiously heavy, falling right into the mass range predicted for primordial ones. Could these be the first direct sightings of the universe's hidden dark matter, these cosmic fossils from the dawn of time finally revealing themselves in a violent, distant collision? After 30 cosmic revelations, we arrive at the ultimate quest. The search for a final theory is the journey to find a single, elegant framework that can seamlessly unite the universe of the very large with the universe of the very small. It is the attempt to write one set of rules that describes the graceful dance of planets and the frantic jitter of quanta. For nearly a century, our two most powerful descriptions of reality have been locked in a state of civil war. General relativity paints a magnificent picture of space-time as a smooth, curving fabric, perfectly predicting the orbits of planets and the bending of light around galaxies. Yet it says nothing about the quantum world. Quantum mechanics, in turn, is a spectacularly accurate guide to the bizarre behavior of atoms and particles, but it treats space and time as a rigid, unchanging stage, completely ignoring gravity. Each theory is brilliant in its own domain, but when their domains collide, the result is mathematical nonsense. At the center of a black hole, or the moment of the Big Bang, where gravity becomes incredibly strong and volumes become incredibly small, the equations of both theories break down, producing infinities that signal our complete ignorance. A successful theory of everything would resolve this conflict, providing a coherent picture of reality at every scale, from the birth of the cosmos to the spin of an electron. The leading contenders for this ultimate prize are the very architectures of reality we have already explored. String theory, with its tiny vibrating loops and hidden extra dimensions, attempts to recast all particles and forces as different notes on a single cosmic instrument. It elegantly includes gravity by describing the graviton as a specific string vibration. Loop quantum gravity takes the opposite path, quantizing the fabric of space-time itself, breaking it into discrete loops to build a universe where the smooth continuum of general relativity emerges from a more fundamental, granular network. Both are monumental undertakings, yet both face profound challenges. String theory, for all its beauty, currently predicts a vast landscape of possible solutions, perhaps 10 to the power of 500 different universes, making it difficult to extract unique, testable predictions for our own. Loop quantum gravity provides a compelling picture of a quantized space, but has struggled to fully incorporate the other fundamental forces and the matter we know. A true theory of everything would be the final key, unlocking a unified understanding of all the hidden layers we have traversed. It would explain why the universe has the exact number of dimensions we experience, why the fundamental constants have their specific values, and whether concepts like time and causality are fundamental or emergent. It would reveal if the holographic principle is a mathematical curiosity or the true nature of reality, and if the multiverse is a necessary consequence of the laws of physics. Finding this final equation would not mark the end of science, but the beginning of a new era. It would be like finally discovering the fundamental grammar of the cosmos, the alphabet with which all of existence is written. We would possess the foundational language to ask entirely new questions about the nature of consciousness, the origin of the universe, and our own place within this vast, interconnected whole. The search for this ultimate theory is the greatest detective story in history, a pursuit that seeks to read the hidden blueprint of everything that ever was or ever will be. From holographic projections to cosmic simulations, we have journeyed across 30 layers of reality, each more mind-bending than the last. We have explored universes born from colliding membranes, felt the ghostly gravity of parallel worlds, and questioned whether our own consciousness is fundamental to the cosmos. The sheer breadth of these ideas reveals a crucial truth. Our universe is not a simple, sterile void. It is a living, breathing question, a mystery wrapped in layers of astonishing complexity. We may not yet possess the final answers, but the pursuit itself has forever changed our perspective. The cosmos is far stranger, more interconnected, and more wonderfully bizarre than our everyday senses could ever suggest. This grand exploration reframes our very existence, transforming us from passive inhabitants into active participants in the greatest story ever told. The search for understanding is what connects us to the stars, so we turn the question to you. After this incredible journey, which of these hidden layers resonates most deeply with your own sense of wonder? Do you find yourself drawn to the elegant mathematics of the holographic principle, or does the infinite branching of the quantum multiverse capture your imagination? Let us know your thoughts in the comments below, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our next dive into the unknown is already waiting.